robot platforms, really. We're not on the robot part yet, programming. We'd like to, but the platform itself has been giving us a little bit of a, what do you say? It was a lot more work than we anticipated. So I brought the platform here for you guys to check it out. So I'll demonstrate it a little bit later. But does anybody know the password to this?
Yes.
I don't know.
Does that need to go to the internet and show stuff? So all these are high school students. So like seniors going to college, not?
No.
Okay. So I'm from CCNY, it's not a community college. People think it is sometimes, but it's the City College of New York. It is a CUNY university with an engineering college in it. So I'm going to show you the site, right? So the reason why I'm showing you this video is because the lights. Oh, you control the lights. Okay, great. So the robot right now, not the robot, the platform right now has some issues. So a few days ago, we were actually having a crawl on the wall and actually fell quite a distance, about like right over there, onto stone floor, and I had to take it apart, put it together, replace the parts, but something is so wrong with it, so it won't perform the way I want it to today. So I'll show you some of the things that we were filming. So this is that, really, you can tell, right? It has cleaner treads, but so basically, I guess this is self-explanatory. I'll just speed through some of this because some of it is kind of intuitive. So as you can see, it's dragging 2 bricks along. And that's kind of together. So basically, it attaches to the wall from the ground, and then it climbs up. And the bricks is a payload. This will demonstrate how much weight it can carry. Each brick is about 8 pounds. So that's about 16 pounds. So, you know, like, if any of you guys lift weights, it's like about 15 pounds. Like, you know, it's weight. It's pretty heavy stuff, but just carry it up just like that. And just, this is me just going up and down. I mean, there's not really much direction I can go on the door, so I'm just going up and down on it. That's about it. I'm trying to get the bricks out of the way here. Alright. Simple machine, right? Not that complicated. Very difficult. Much more difficult than I anticipated. Yeah, you have to clear a lot in your head pressures and the kinds of like dynamics between like a suction motor and suction fans and things like that. Between pressure and airflow, like air volume flow, that kind of thing. It's kind of like no more pressure, you get less airflow. Seems kind of obvious, but it's finding the right devices, the right parts that serves your needs, that kind of thing. It's a lot of back and forth. And so that's about it that I can show you. How many of you guys are going into the engineering field? Planning to? Oh, there's a lot of you. What kind? Electrical. Electrical? There's a lot of electrical. Are you? Mechanical? Awesome.
Computer science.
Yeah. Computer science, okay. Do we have?
All three. All three.
All three? How are you going to do all three?
I love all three.
Oh, try. You're gonna need 3 people to do the engineering papers. I'll tell you what, engineering school is a lot of work. It's like twice of that of any other discipline, undergrad. Seriously, it is. Maybe except for like pre-med, but that's a lot of like memorizing books. Engineering is completely different. You'll never take a multiple choice exam ever again from day one once you enter engineering school. Just letting you know, heads up. Do we have biochemical? No? Oh, that's a shame. Which one?
I want to do chemical engineering.
Bioengineering? Cool. Bioengineering is like a cousin of mechanical, but they're cool too. Alright, well, if you have any questions about engineering school, you can ask me, and after that, I'll show you, I can still demonstrate some things that, I can still turn this on and demonstrate the kind of abilities it has. So, if you have any questions, yeah.
Can I ask a question about that?
Okay.
So
I should put it up top here.
So like stick on the wall like that. Is it different for like different materials? Like how does it know whether it's going up like?
Good question. So this was designed specifically to climb multiple kinds of surfaces, because if you look up on YouTube, for example, like wall climbing machine, a bunch of them will come up, right? But a lot of times they can only work on certain surfaces. For example, there's magnetic ones. So they can only work on ferromagnetic surfaces, like iron or whatever. Right? Some tanks are made out of steel. You can climb up certain types of steel tanks. Stainless steel is not magnetic, so they can't climb those. Brick walls they can't. Some of them only work on smooth surfaces, maybe like kind of a surface like this or glass, right? This was designed, or we tried to design it so that it can climb up all sorts of surfaces, like brick, masonry, cinder block, pitted walls, concrete, smooth surfaces as well, all sorts. And a big challenge was making this tread. And the tread, there's a lot of engineering going on in this tread that allows it to do that. It's a composite tread made out of 2 different kinds of material that allow it to do it. It's not perfect, but it's like 5th generation tread designs that we went through. So yeah, we manufactured it in-house as well. So kind of proud of it. Yeah.
They use suction cups, right?
They're not exactly suction cups.
Similar?
But, yeah, I'll show you how it works.
So-
a little later. You had a question?
Oh, well, I was kind of asking, like, what about that sticks to the wall? Is it like a special material? Like,
No,
is
it's
it
not
suction?
material based, it's suction fan based. Yeah, the sound was off in this video, but it makes kind of a bit of a noise when it's running. And it's basically because it uses 2 high pressure impellers to draw the air out in through the holes.
What's like the weight of that? What's the weight of that?
How much does this weigh?
Yeah.
It's kind of heavy. It's about 36 pounds.
Oh, okay.
Yeah.
You must be using like powerful motors. To,
Yeah.
Yeah.
Well,
That must have cost you quite a bit, right?
okay, so on that, right? So what's pressure? What's the definition of pressure? For example, PSI, what does that mean?
Pressure per square inch.
Ounce per square inch.
Force per area.
Yes, force per area, right? So what does that mean? So for per unit area, you get a certain number of force, right? So if you have 1 psi, right? Suppose a motor, right, or a pump can produce 1 psi maximum, right? And you'll have 1 inch of square space that it evacuates. What's the force that it can have? 1 square inch.
1 pound. Force.
1 pound, right? Because 1 psi. The motor can only produce 1 psi. So if you have a square inch suction cup, it's only 1 square inch. You only get 1 pound. But using that same pump, you have a suction cup that's this big. That's like 50 square inches, right? How much pounds can that little pump have?
50.
50, right? Same motor, right? It's interesting, right? So that's why there's a limitation on this and on how small it can be. That's why it's this large. Because we wanted to make the surface area as large as we can, or what's reasonable, so that we can have a large surface area to have it heat, have the adhesion. So what happens is it gets heavier. We have to put on bigger motors. So it's kind of a curve. So we hit a point in the curve where there's enough power that we generate out of a reasonable amount of weight for the motors, so that we can pull up 15 pounds of payload, which was our target. So it's an engineering problem in that sense. Okay. Yeah.
How did you make the treads?
Oh, okay. Well, that's a story all on its own. Okay. So this is made out of a silicon mold. Have you guys played with Smooth On? Anybody? So Smooth On is a company that produces kind of like these porable like polymers, silicon rubbers, plastics, things like that. So silicon is a really tough rubber synthetic material, but it's also very flexible. Right? So the reason why we need flexibility is so that it can conform to the pits and grooves and bumps of an uneven wall. So that's why we use it. But that is still not conforming enough. So what we had to do was we had to create a skin of silicon. And within that, there's a foam silicon foam. It's a different kind of silicon foam. So it's a three-step molding process. So we first create the skin with one mold. We remove one side of the mold. We pour in the foam silicon, and we cover it with the second mold. And after that, we take it apart. We adhere it to this is a spring steel sheet that we laser cut. And so that serves two purposes. It's to provide tension, because if you look here, we tension the belt by having one section move to, against each other. So it has to resist stretching. It also has to have smooth surface on this side, because the secret of this machine is that the vacuum suction actually slides along the tread while maintaining suction. So it has to be a smooth surface. So that's why we use spring steel on the inside, and also flexible. Spring steel is able to turn around in this radius and still be strong, not bend and deform constantly. Yeah.
How did you came up with an idea to do it?
So, the person I work for, he's a professor that works at BSE NYC. He's been working on wall climbing robot for a very long time. He started work on it like 10 years ago, 9 years ago. And so what happened was he collaborated with this is kind of getting into politics, but I guess I should talk about that too. So he collaborated with another professor, and he had a patent under both of their names. But since then, they've kind of fallen, didn't agree on certain things. They decided to go their separate ways. So he wanted to continue work on that. He couldn't use the same patent. So this is a completely different machine than the previous machine they worked on. So that's why I built this. There are better ways, I believe. I shouldn't say this, but there are better ways to climb a wall. I think the first iteration, not the first iteration, but the machine that they made first, with the first group, has a better design, but I was asked to create a machine that does the same thing, completely different. So this is the result. Yes?
How did you come up with the methods of like climbing up the wall?
What do you mean?
Like, you said
Alright,
the
cool.
secret to the machine is the sliding.
Oh,
So how did you
well,
like come up with that idea?
It's you kind of think in your head, you kind of imagine it, because that might work. You kind of build test rigs. They don't have motors in it, but it's like you create like a test, because you gotta get this thing out quick. But you don't know if that idea works. So you make something simple. There's no motors, there's no controls in it, but you should test it to see if that mechanism works. This one kind of applies to maybe like mechanical things, but I'm sure there's parallels in other fields too. But you make a quick iteration just to test that specific property that you have. And you just test it out, it goes, oh, that kind of works. You kind of go with it, develop it, and it's always an iterative process. This is not the very first one that came out. We built machines that kind of look like this, with less features, different features. And this is kind of like, oh, the children of them all, I don't know. There were lots of, there's a box with scrap in it that kind of look like this. It's, yeah, that's, I guess what I can say, yeah.
If it like hits a corner or something, is it able to go past the corner? Like,
So it can do this corner off the ground, it can't do this onto the ceiling.
oh,
So that's an interesting challenge.
is there any reason why I can't do that?
Yeah, so when it's going on the wall, right? You see these fans on top of here?
Yeah.
So it gives a slight push to the robot. So what it does is we turn these on so that when it's going like this, it prevents it from tipping over like this. But that's all it can do. There's not enough force on these to have it only using this pushed against the wall. But now think about it going from the wall to the ceiling. It has to break the seal, and it has to be supported by something else. These aren't going to do it. So maybe we had something like 10 times the power of these. We could do it. Other than that, yeah.
Does it only go up and down, or can you have it?
Yeah, this steers, kind of like an
Okay,
track.
so could you go from like one wall to the other, like around that sort of corner?
Like this,
Yeah.
like around that corner. No, you can't. But it'll go around a rounded surface. For example, a tank, like silos, cooling towers for nuclear power plants, dams that are curved concave. So it can do kind of large structures. This was actually intended to service and inspect those kinds of structures, like large concrete structures. Yeah.
How fast the
I'd say about 1 meter per second. Not very fast at all. But I haven't tried to exceed it because I don't want to push it because then it'll fall and break this up. So yeah.
Did you build this on CAD before you started building?
Yes. Majority of this was designed on SolidWorks.
SolidWorks?
Yeah. What do you guys use?
Google SketchUp. Google SketchUp.
Oh, okay. SketchUp. It's free, right?
Yeah.
Why not? It serves its purpose. But yeah, we use a software called SolidWorks. It's very popular in school because it's very easy to use, but it's prohibitively expensive. It's very expensive. Like the pro version costs $10,000, so yeah, it's kind of expensive. Yeah, I know, right? Can you imagine? Piece of software, $10,000. You need 20. So yeah. Anyway, any more questions? Alright, so I'd like to do a little demonstration. I'm actually not sure how much battery is in here, but I can, whoever wants to, you can come up and come take a look. I'll do a suction demonstration. I'll show you what's wrong with it with this.